Good morning students. Today we will discuss about polarity of the bonds and dipole moment. Topic is polarity of the bonds and dipole moment. So polarity, what is polarity? What is dipole moment? So here we know that one covalent bond is of two types. Covalent bond is of two types. Covalent bond is two types. First one is non-polar covalent bond. Non-polar covalent bond. And second one is polar covalent bond. Polar covalent bond. So non-polar covalent bond means if the covalent bond exists in between same type of atoms, HH, Cl, Cl, Br, Br, oxygen, oxygen, nitrogen, nitrogen. So these all are homogeneous atoms. They are similar atoms. If the covalent bond is formed between similar atoms, then the covalent bond is called as non-polar covalent bond. So this is similar atoms. Similar atoms having same electronegativity. So having same electronegativity. So if they have same electronegativity, the bonded pair is equally distributed in between two atoms. Equally distributed between two atoms. So therefore there is no polarity. There is no polarity between atoms. So but in case of polar covalent bond, if the covalent bond is formed between dissimilar atoms. Dissimilar atoms means they having different electronegativity. If they having different electronegativity, what happened? The bond pair is slightly attracted by one of the atom. Slightly attracted by one of the atom. I will take one example here. HCl. The electronegativity of chlorine is more than hydrogen. Therefore, this bond is slightly attracted by chlorine. So, this bond pair is slightly attracted by chlorine. We get negative charge, get positive charge here. Therefore, here this positive pole is called positive. Two poles will observe here. This is positive pole. This is negative pole. So this type of covalent bond is called polar covalent bond. So polar covalent bond and this molecule is called polar molecule. The property is called as polarity. So we are observing this different dissimilar atoms. Dissimilar atoms means they having different electronegativity. So in case of polar molecule, the property is called as polarity. The molecules which exhibit polarity, they also exhibit one property. That property is called as dipole moment. So what is dipole moment? We will discuss in this class. So here I will explain dipole moment. So here you take any molecule here, HCl. So it has a high electronegativity, it has low electronegativity. Therefore it gains positive charge, it gains negative charge. Therefore, now we will discuss about dipole moment. So dipole moment mu equal to charge on pole into distance between two poles. So charge is intimated by Q and distance is D. So simply we are changing the product of charge and distance of polar molecule is called as dipole moment. So the product of charge on one pole and the distance between two poles is called dipole moment. So it is denoted by m or mu. So units are dipole units. Dipole is intimated by D, capital D. So one dipole equal to, so here charge means coulomb or ESU. Coulombs or ESU, electrostatic units. Distance means centimeters and meters. Therefore, units are charge units into distance units. So that is the units of dipole. Therefore, dipole moment is equal to the product of the charge on one pole and distance between two poles is called as dipole moment. So dipole moment is intimated by m, small m or mu. So whatever it may be, in some books they are intimated as m, in some books they are intimated as mu. So after that, so units are dipole units. One dipole equal to equal to 3.33564 into 10 power minus 13 coulomb meters. Coulomb for Q, M for distance. This is 1. After that, 10 power minus 18 ESU centimeters. 10 power minus 18 ESU centimeters. So this is our CGS and MKS. So SI system this is and CGS system this is. In SI unit this one and CGS units this one. So this is one dipole. So actually, dipole moment is a vector quantity. So actually it is a vector quantity. So it is intimated by arrow mark, positive end to negative end, like this. So vector quantity. So it is a vector quantity and intimated by arrow mark, crossed arrow mark, crossed at one end. So positive end to negative end, like this we are intimated. So this is about introduction of dipole moment. So after that, so here we have one more discussion is the vector sum of the bond dipoles of various bonds. So for example, multiple bonds are there. So it is the vector sum of the bonds, multiple bonds. For example, here, this bond. A is there, C, D, E, like this. So this is vector sum. In this direction, in this direction, in this direction. In this direction it is mu1, it is mu2, here mu3. The total mu equal to mu1 plus mu2 plus mu3. So if in this direction minus mu4, like that. So vector sum of the various bonds. Vector quantity means in physics you know that one vector quantity means like this. In spatial arrangement also we are considered. So this is about dipole moment. So I will take calculation of resultant bond moment. Next one is calculation of calculation of resultant bond moment. Calculation of resultant bond moment. So here A C. So here in this direction this is mu1, in this direction mu2, this is theta. So mu r is equal to under root of mu1 square plus mu2 square plus 2 mu1 mu2 into 2 cos theta. So this is the formula. So 2 mu1 mu2 cos theta. So this is the formula. 2 mu1 mu2 cos theta. Theta equal to bond angle. Theta equal to bond angle. So this is the mu1 square plus mu2 square plus, so a square plus b square plus 2ab cos theta, like that formula. So in this direction we are considered, in this direction we are considered. So therefore mu r is calculated by mu1 square plus mu2 square plus 2 mu1 mu2 into cos theta. Theta here bond angle. Here theta equal to bond angle. Bond angle. By this we can calculate resultant bond moment. Resultant bond moment we are calculated by using this formula. So this is about vector quantity. That's why we are considered in this direction. In this direction. So this is about calculation of resultant bond moment. Calculation of resultant bond moment. Now we discuss about type of molecule. Type of molecule and example. Dipole moment is possible or geometry. I will take few examples. I will take and I will explain here. I will take molecule. Type of molecule. Type of molecule. AB type. So for AB type, I will take example HF, HCl, HBr, HI, H2. So what is the shape of these all molecules are linear. This is also 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 linear. HH, hydrogen. So here it has less electronegativity than this one. Therefore it gets positive charge, it gets negative charge. So it is positive charge, negative charge. Here also positive charge, negative charge, positive charge, negative charge, positive charge, and here also negative charge. No, here only there is no charge at all. In case of hydrogen, so hydrogen are same atoms, therefore linear molecule. Therefore there is no polarity. Therefore these molecules are exhibit polarity. Polarity is observed here. There is observed polarity. So there is no polarity in this because these molecules are. Therefore these are having mu is not equal to 0. In case of this, mu value is there or 0.10 or something, 1.78 or 1.07, 0.70 something. So they having value. So 1.70 something like this, they have a value. Therefore, mu is not equal to 0 here. Mu is not equal to 0 here. Mu is not equal to 0. Mu is not equal to 0 here. but here mu equal to 0 because there is no polarity. If there is no polarity, there is no dipole moment. But here there is some value. Not equal to 0 means there is a value. That means here there is a value, there is a value, there is a value, there is a value. But in case of linear molecule, there is no value. So this is about type of molecule. We are taking so many examples. We are discussing so many examples of dipole moment. Good morning, students. Today we will discuss about dipole moment and its applications. So first we will discuss about type of molecule. After that, example. Next one, dipole moment and shape or geometry. So here geometry. Same table I will repeat here also. Type of molecule. Example, mu and geometry. Geometry means shape of the molecule. So here, first one is AB type. So molecule is AB type. So AB type example is HF, HCl, HBr, HI, H2. So HF, HCl, HBr, HI, H2. So these are examples. So these are shape of these molecules is geometry is linear. This is also linear. This is also linear. This is also linear. This is also linear. But here, for this, dipole moment is 1.78 divide. This is 1.07 divide. This is 0.74 divide. This is 0.08 divide. But for hydrogen molecule is 0 because it is non-polar molecule. It is a non-polar molecule. Therefore, its dipole moment is 0. The dipole moment is 0. So, like this we will take so many examples here. We will discuss about so many examples. This is, so actually here the electronegativity of fluorine is more than hydrogen. The electronegativity of fluorine is more than hydrogen. Here also the electronegativity of bromine is more than hydrogen. Here also different elements, dissimilar atoms. Therefore, these molecules are called polar molecules. These molecules are called polar molecules. For polar molecules, we have dipole moment. We will calculate dipole moment. But in case of hydrogen molecule, it is non-polar molecule. And the bond between two hydrogen atoms is also non-polar bond, polar covalent bond. It is non-polar covalent bond. Therefore, for non-polar covalent bond, mu n equal to 0. Mu n equal to 0. Same thing I will explain here for molecule AB type, AB2 type. So AB2 type molecule is, I will take 3 examples here. H2O, H2S and CO2. So here CO2 is also, the shape is bed shape here. For this 1.85 divide 0.95 divide, because they having the shape bend shape like this, bend shape. So I will draw the structure here. So this is the structure of H2O and this is the structure of H2S. With 2 lone pairs here. Here also 2 lone pairs. But in case of carbon dioxide, so in case of carbon dioxide, mu equal to 0 because it is linear shape. It is linear shape. So linear shape means like this. So it is vector quantity. It is vector quantity. Therefore, net dipole moment of CO2 is 0. So here, this is direction is there. Here, in this direction, we are observing the dipole moment. Ground moment is observed in this direction. But in case of in this direction plus in this direction minus, net dipole moment is 0 for linear molecules. For linear molecules, net dipole moment value is 0. So like that, we will calculate for AB3 type molecule and also AB4 molecules. After that, I will take AB3 type molecule. So AB3 type molecule examples are NH3, NF3, BF3. So here the values are 1.47, 0.23. Here 1.47, 0.23. Here for this BF3 is 0. So why 0? So the shape of this molecule is lone pair is observed here. Lone pair, trigonal plane pyramidal. In case of NH3, the shape is trigonal pyramidal. That is important. So trigonal pyramidal means here the shape is like this with one lone pair. We are observed one lone pair. But in case of NF3 also same shape, but in opposite direction. So whatever it may be, the sum of dipole moment is vector quantity. Therefore, in case of NF3, the shape is like this. So here, we are observed in this direction. But whatever it may be, there is a dipole moment for NF3 and NH3. But in case of BF3, so NF3 shape molecule is also trigonal pyramidal. But BF3 shape is trigonal planar. So trigonal planar. Therefore, for the trigonal planar, by the shape in this direction, same direction we are observed. So both will cancel. So if the opposite directions are whatever it may be, trigonal planar means it will net dipole moment is 0. So this is about and also AB4 molecule. I will observe one more example is there. AB4 molecule. So AB4 molecules are CH4, CCl4, CHCl3. So here for CH4 0, CCl4 0, but CHCl3 1.05 dipole. But shapes are same, tetrahedral, tetrahedral, tetrahedral. So tetrahedral, this is also tetrahedral, this is also tetrahedral. So but because of hydrogen, the direction is same direction will observe. So one height because of hydrogen, the vector quantity we get some value for that 1.04. But here is opposite direction, both are cancelled here. So this is about. So in CHCl3, polarity will happen. We are observing polarity or dipole moment or bond moment we are observing. But in case of CH4 and CCl4, we are not observed any bond moment. So that's what these are. For linear molecules also having dipole moment. Bent molecules, in some cases we are observed in case of linear molecules, if the dissimilar atoms are form the linear structure, they having dipole moment. So these all are examples for the dipole moment. After that, we will discuss about the applications of dipole moment. Next one is applications. So here, applications of dipole moment. So here, what are the applications of dipole moment? First one is, we can determine the geometry of the molecule. First one is determination of geometry of molecule. So for example, water molecule, mu is not equal to 0. We have some value. But CO2 mu equal to 0, no value. That means mu is not equal to 0 means mu equal to 1.85 dipole. Therefore it is not linear. So CO2 is linear. There is no dipole moment for CO2 molecule. So by knowing the value, if dipole moment value is there, that means that is not linear molecule. But the simple way to identify that one. So here CO2 molecule doesn't have any dipole moment because its dipole moment value is 0. Therefore, dipole moment value is 0 means the shape of the molecule is linear. So shape of the molecule is linear because mu equal to 0. For example, if you take water molecule, for water molecule bend shape means it has dipole moment. So by knowing the value of dipole moment, we can separate element. So for this, it has net dipole moment is there for net dipole moment is also there for water molecule. So therefore, it is first application is it is useful to determine the geometry of the molecule. So this is first one. Second one, polarity of the molecule. Polarity of the molecule. Second one, polarity. You know that one, what is polarity? So if the covalent bond is formed between dissimilar atoms, the molecule is considered as polar molecule and the bond is considered as polar covalent bond. So here, if the molecule is polar molecule, then only it has dipole moment. Therefore, if it has dipole moment, then it has polarity. Therefore, we can separate polar molecules and non-polar molecules by knowing the value of dipole moment. If the molecule has dipole moment value, then it is polar molecule. Polar, for polar molecules, mu is not equal to 0. Therefore, they have polarity. They have polarity. For non-polar molecules, mu equal to 0. Therefore, no polarity. No polarity. This is also one of the important application of dipole moment. And also third application is we can separate symmetrical molecules and unsymmetrical molecules. So how can we separate symmetrical molecules and unsymmetrical molecules? For example, so it is also useful to distinguish or differentiate symmetrical molecules, symmetrical molecules and unsymmetrical molecules. I will give an example for this. CO2 is mu equal to 0. Therefore, it is a symmetrical molecule. It is a symmetrical molecule. H2O is mu is not equal to 0. Therefore, mu equal to 1.85 divide. Therefore, it is unsymmetrical molecule. It is unsymmetrical molecule. Therefore, what is, by knowing the value, if the molecule having mu value or mu is not equal to 0, then that molecule is non-symmetrical molecule. For CO2 mu equal to 0, that means it is a symmetrical molecule. Symmetry we can observe like this. For H molecule, hydrogen molecule also mu equal to 0. Therefore, it is also symmetrical molecule. So this is a very important thing, because for water molecule we have mu value 1.87 divide. So 1.87 dipole means it has a particular value. Therefore, it has particular value means it is a symmetrical, non-symmetrical molecule. CO2 is a symmetrical molecule. So these are the most important three applications of dipole moment. So after that we will discuss about more applications of dipole moment. Good morning, students. Today we will discuss about applications of dipole moment, part 2. So already few applications are discussed before. Now we are going to discuss about applications of dipole moment 2. So applications of dipole moment 2 means, so this is also other applications. Already we have discussed some few applications are covered before class. So just we are discussing about some properties also. So NH3 has higher dipole moment than NF3. So this is NH3 has higher dipole moment than NF3. Why? Here this is question. NH3 has higher dipole moment. When you observe the structure of NH3, so this is the structure of NH3. So here next we'll compare with NCl3 also we have compared. NCl3 also we have compared. And NF3 here this is nitrogen trifluoride. So here the bond movement is in this direction. So here also the bond movement in same direction like this. So therefore in these two cases bond movement in same direction, but in case of NF3, here bond movement is there in this direction, in this direction. So this bond movement and this bond movement, two bond movements get cancelled. Resultant bond movement is the sum of these two bonds only. Therefore here 4 bond moments are there. 4. This is 1, 2, 3, 4. For example, this is +1, +1, +1, +1. Total +4 bond moment. Example I am giving. Here also same. But here this is +1. This is +1, +1, +1. Here -1. This will cancel. How much we get? +2 only. Resultant bond moment is +2. That means it has less bond moment than NH3. So NH3 and NCl3 because so actually dipole moment is a vector quantity. So therefore bond movement vector quantity means is the sum of the all vectors. So here when you compare these three, so it has more. These two are having more when compared to NF3 because the bond movement in the same direction in case of NCl3 and NH3. So this is also important. One of the application. So by knowing this one, we can confirm the molecules also. So molecules which having more dipole moment, they having more polarity. So that is also one of the important thing. After that, second one is cis and trans isomers. Cis and trans isomers also separated. For example, cis isomer and trans isomer, I will explain here. Cis isomer, and trans isomer. Cis isomer and trans isomer. This is cis isomer. This is trans isomer. So here, so bond movement is in this direction, in this direction, in this direction, in this direction. Therefore, bond moment is not equal to 0 in case of cis isomer. But in case of trans isomer, here in this direction, in this direction, in this direction, in this direction. So here, sorry, in this direction. So two are, this is and this is get cancelled. This is get cancelled. So in this direction is also there, in this direction is also there. Therefore, mu equal to 0 for trans isomer. So for same direction, in this same direction, bond moment is in same direction. So bond direction is in opposite direction. So opposite direction, both will get cancelled here in case of. So what is the use of this dipole moment? Means we are, by knowing cis isomers are having more polarity, by knowing these values, means we can confirm that cis isomer having more polarity than trans isomer. That we confirm that. So this is also very important. We know that when cis isomers means identical groups are adjacent to each other. So here identical groups are groups are adjacent to each other. So here identical groups are opposite to each other. Identical groups are opposite to each other. So this is also one of the important. So because of dipole moment, we confirm that. So cis isomer having more polarity than trans isomer. In case of trans isomer, opposite directions, identical groups are in opposite direction. Here, same direction. So if it is considered as plane, so here same. These chlorine atoms are same side of the plane here. Here, chlorine atoms are opposite sides of the plane. Therefore, this is also very important thing to separate cis isomer and trans isomer. After that, Just we'll compare the dipole moment of ortho, meta, para isomers. So ortho, meta, para isomers, just we'll compare the which one is having more polarity. So I will explain here. So here, cis ortho isomer, ortho, meta and para isomer. So ortho dichlorobenzene, meta dichlorobenzene and para dichlorobenzene I will take here. So here, this is ortho dichlorobenzene, this is meta dichlorobenzene and it is para dichlorobenzene. So here, when you observe the values for ortho 2.53 divide, for meta 1.48 divide, but in case of para mu equal to 0. So here, in this direction we are observing, net dipole moment is 0. So therefore, ortho isomer having more than meta than para. So here, because ortho isomer having the same direction, so therefore, when we compare to this one, ortho is greater than, meta is greater than para. So all para isomers are not having the same type of mu. I will take one example. If the same group, here the same groups are there, chlorine, chlorine. So what if you take, so instead of chlorine, we are taking bromine. So bromine means, so bond movement is not cancelled by each other. Bond movement, not cancelled by each other. So here bond moment is not cancelled. Therefore, mu is not equal to 0. In case of chloro, bromo, benzene, 1 chloro, 4 bromo, benzene, it has dipole moment. So like this, we can confirm the which one having polarity more, which one having polarity less. By this, by the dipole moment, we can identify. So therefore, in case of ortho, meta, para isomer, ortho isomer having more dipole moment than meta and para. So in case of para, bond moment is cancelled by each other. Net dipole moment is 0. So net dipole moment means in one direction plus 1, in other direction, opposite direction, minus 1. Therefore, net dipole moment will cancel by both bond moments. Therefore, it is also one of the important. So after that, Good morning students. Today we discuss about numericals of dipole moment. So numericals. So these numericals are based on two formulas. First formula is dipole moment equal to, so 2 into bond moment into cos theta by 2. So here theta equal to bond angle. After that, second formula, percentage ionic character equal to observed dipole moment by calculated dipole moment into 100. So therefore mu observed by mu calculated into 100. So these formulas based on we will do the problems. First one is dipole moment equal to 2 into bond moment into cos theta by 2. Theta equal to bond angle. What is bond moment means? For example, this is X bond. Here A and here bonded atoms. This each bond having some moment. That moment is called bond moment. So now we discuss about. Now we will do the first problem. This is first problem. I will explain this problem. So first problem is based on percentage ionic character. So the dipole moment of HBr is 2.60 into 10 power minus 30 cubic meters. And inter-atomic spacing is 1.41 angstroms. What is the percentage ionic character of HBr? So here, HBr molecule is there. So now we will write the first formula. Percentage ionic character equal to mu observed by mu calculated into 100. This is the formula first. So mu observed is given how much? So mu observed dipole moment is given 2.60 into 10 power minus 30 Coulomb meters. So mu observed is given. Just we are calculating mu calculated. So mu calculated is equal to charge into distance between two poles. Charge means electron charge we are considered. That is 1.60 into 10 power minus 19 coulombs, and distance is given 1.41 angstroms. When it is converted into 1.41 into 10 power minus 10 meters. So after calculation these two values, we get 1.60 into 1.41 into 10 power minus 29. The value is 2.26 into 10 power minus 19 Coulomb meter. This is mu calculated. So here, first you have to write the formula of percentage ionic character. So percentage ionic character equal to mu observed by mu calculated into 100. Therefore, mu observed is given. This is second step. Already given in this. Third step is mu calculated equal to charge into distance. Charge is Coulomb distance. 1.60 into 10 power minus 19 into 1.4 into 10 power minus 10 distance. After that, so you have to substitute in this equation percentage ionic character is equal to mu observed by mu calculated into 100. So mu observed is how much? 2.60 into 10 power minus 30 by, so mu calculated here how much? 2.26 into 10 power minus 90 into 100. So after substituting all these values, we get the value 11.5% we get. So 11.5%, this is the answer. So this molecule, HBr molecule, actually it is a covalent molecule. So covalent bond is there here. It get negative positive charge, it get negative charge. So 100 minus 11.5 is covalent character. So means, so 100 minus 11.5% is covalent character and 11.5% is ionic character. So this is about the problem. So percentage ionic character. So this is, by in this method we can calculate. After the second problem is based on bond moment. I will take different problem, bond moment. So next problem is based on bond moment. Dipole moment of second problem. Dipole moment of stress is 0.95 divide. 0.95 divide. Find the SH bond moment. Find the SH. Find the SH bond moment. SH bond moment. SH bond moment. Bond angle in H2S is bond angle. Bond angle in H2S is 96 degrees. And cos 45 degrees is cos 48 degrees is 0.66. This is the given data. So we know the formula. Dipole moment equal to. So what is the formula? 2 into bond moment. 2 into bond moment. 2 into bond moment into cos theta by 2. This is the formula. Bond moment into cos theta by 2. After that, 2 into bond moment. So which bond moment? SH bond moment into cos theta by 2. I will write the formula. Dipole moment of H2S. So here, dipole moment of H2S is given 0.95. 2 into bond moment is, we have to calculate SH into 96 by 2. Cos 96 by 2. So that is 2 into mu SH into cos 48 degrees. So 0.95 into 2 into mu SH into 0.66. So here 0.72 we get mu SH equal to 0.72 divide. So here, this is sulfur and H2S, this theta is given, that is 96 degrees, and you have to calculate this bond moment. This bond moment value is, SH bond moment value is 0.72 dipole. So 0.95 is the dipole moment. This is the dipole moment is given. So dipole moment equal to 2 into bond moment into cos theta by 2. This is the formula. So this is also second model of dipole moment. Second model of dipole moment. After that, third model, we'll do the third problem. Same percentage ionic character. I will write the formula here. Second problem is the dipole moment. Third problem, I will take third problem. The dipole moment of HBr is next problem. The dipole moment of HBr is the dipole moment of HBr is 0.78 into 10 power minus 18. 0.78 into 10 power minus 18 ESU centimeters. The bond length of HBr is the bond length of HBr is 1.41 angstroms. 1.41 angstroms. Calculate the percentage ionic character of HBr. So here we know the formula. So HBr is here Br minus plus the distance is given how much? 1.41 angstroms. So what is the formula? Percentage ionic character equal to mu observed by mu calculated into 100. This is the formula. So mu observed is given 0.78 into 10 power minus 18. So here, after that, mu calculated we have to calculate. So mu calculated is equal to, so mu calculated 4.8 into Q into D. So Q into D, distance. This Q is not given in ESU. 4.8 into 10 power minus 10 ESU charge. After that, D, distance. Distance is 1.41 into 10 power minus 8 centimeters. Here, centimeters is given, that's why I have taken the centimeters. After that, 4.8 into 1.41 into 10 power minus 18. This value. So after simplification, we get this value 6.768. 6.768 into 10 power minus 18 ESU centimeters. This is mu calculated. So after that, percentage ionic character equal to mu observed. Mu observed is how much? 0.78 into 10 power minus 18. Here mu observed is given. So we have calculated mu calculated 6.768 into 10 power minus 18 into 100. So 0.78 by into 100 by 6.768. That will simply we get 11.52 percentage we get. So 11 point percentage ionic character, remaining is covalent character. So these are the problems, percentage ionic character and bond moment of the covalent molecules. So percentage ionic character is calculated by using this formula. So these are the numericals of dipole moment. So first formula is mu dipole moment into the product of charge and distance. This is one formula. Percentage ionic character, second formula. Bond moment, third formula. By using these three formulas, numericals are related to these three formulas only. So in case of dipole moment, three formulas are using to calculate the numericals of the dipole. So this is enough to calculate numericals of dipole moment. Good morning students. Today we will discuss about numericals of dipole moment. Numericals of dipole moment. Numericals of dipole moment. So these numericals are based on three formulas. First formula is dipole moment equal to charge into distance. This is first formula. Charge equal to Q and distance equal to D. Second formula, dipole moment equal to 2 into bond moment into cos theta by 2. This is second formula. Here theta equal to bond angle. So here theta equal to bond angle. One more formula is there, that is percentage ionic character. This percentage ionic character is calculated by mu observed by mu calculated into 100. So mu observed by mu calculated into 100, that will give percentage ionic character. So based on these formulas we can do the problems of dipole moment. Now first we will discuss about first problem. So dipole moment here is given one problem. I will explain first problem. First problem is the dipole moment of HBr is 0.78 into 10 power minus 18 ESU centimeters, and the bond length of HBr is 1.41 angstroms. Calculate the percentage ionic character. We already given one formula, that is percentage ionic character equal to percentage ionic character equal to mu observed by mu calculated into 100. So here mu observed is given, mu observed equal to 0.78 into 10 power minus 18 ESU centimeters. So ESU units are for charge, centimeters are for distance. Therefore, now we will calculate the mu calculation. Calculated dipole moment equal to charge into distance. Charge is not given, but here electron charge is ES2. How much? 4.8 into 10 power minus 10 ESU. Charge is, distance is given 1.41 into 10 power minus 10 minus 8 centimeters. Therefore, this value is 6.768. 6.768 into 10 power minus 18 ESU centimeters. This is mu calculated. This is mu calculated. After that, so mu calculated is calculated here. Now we will substitute this value in the percentage ionic character formula. Therefore, percentage ionic character equal to mu observed by mu calculated into 100. So mu observed is given how much? 0.78 into 10 power minus 18. Mu observed here is given. So mu calculated is 6.768 into 10 power minus 18 into 100. This will get cancelled. 0.78 by 6.768 into 100. So after simplification of this value, we get the value is 11.52 percentage. 11.52 percentage of ionic character. So this is the problem. Percentage ionic character. So after that, I will take one more example for this. Second example I will take. So like this we can calculate the problem. The dipole moment of HBr is 0.78 into 10 power minus 18 ESU centimeters. The bond length of HBr is 1.41 angstroms. Calculate the percentage ionic character of HBr. This is the problem. So percentage ionic character equal to mu observed by mu calculated into 100. So mu observed is given, the value is 0.78 into 10 power minus 18 ESU centimeters. We know that one dipole moment is the product of charge and distance. Therefore here charge is given in ESU. So ESU is value of electron charge is 4.8 into 10 power minus 10 electrostatic units, and angstroms is 1.4 into 10 power minus 8 angstroms. So by the calculation we get mu calculated equal to 6.768 into 10 power minus 18 ESU centimeters. Now the percentage ionic character equal to mu observed by mu calculated into 100. So mu observed equal to 0.78 into 10 power minus 18 by 6.768 into 10 power minus 18 into 100. 0.78 by calculating we get 11.52 percentage. This is about first problem. Second problem is, I will write here. Second problem, the dipole moment of HBr is the dipole moment of HBr is, second problem, the dipole moment of HBr is 2.60 into 10 power minus 30. 2.60 into 10 power minus 30 coulomb meters. And the interatomic distance is and the interatomic distance is Distance is 1.41 angstroms. Calculate the percentage ionic character of HBr. Calculate the percentage ionic character of HBr. So here in meters is given. So first we'll write the formula. Percentage ionic character equal to mu observed by mu calculated into 100. So mu observed is given how much? 2.60 into 10 power minus 30. Now we calculate mu calculated. So mu calculated equal to charge into distance. Charge is in coulombs is given 1.60 into 10 power minus 19 and distance is 1.41 into 10 power minus 10 meters. Therefore 1.60 into 1.41 into 10 power minus 29. So it is coulombic meter. So this value is, we get 2.26 into 10 power minus 29 coulombic meter. This is mu calculated. So after that, this is substituted in this equation. Percentage ionic character equal to mu observed by mu calculated into 100. So mu observed is how much they are given in the problem. Therefore mu observed value is 2.60 into 10 power minus 30 by mu calculated is 2.26 into 10 power minus 29 into 100. So this value we get approximately 11.5% of ionic character. So this is the way to find the percentage ionic character. So HBr molecule is actually covalent molecule, but in covalent molecule some percentage of ionic character is also there. That value is 11.5. So 11.5 means how much? 88.5 is. So this is 88.5 plus 11.5. How much here? So this is total 100 percentage. So HBr molecule. In case of HBr molecule, 88.5% is covalent character is there and 11.5% of ionic character is there, because two ions are there. Here this is negative ion, this is positive ion. Therefore if they are asking covalent character, 100 minus 11.5 is the covalent character. Therefore if they are asking here, that is ionic character is 11.5%. If they are asking covalent character, 100 minus 11.5 gives that much. 88.5 is the covalent character of HBr. So like that we can calculate the percentage of ionic character and percentage of covalent character is calculated by using this formula. After that, one more formula is a bond movement. Just once you see the problem related to bond movement. So this is also related to percentage ionic character. After that, next problem is based on bond movement. Next problem is based on bond movement. So here problem is, I will write here the dipole moment of H2S is, third problem, dipole moment of H2S is 0.95 divide. 0.95 divide. Find the SH bond moment. Find the SH bond moment. SH bond moment. SH bond moment. Bond angle in H2S is, bond angle in H2S is 96 degrees and cos 48 degrees is 0.66. The value is here. So now we calculate bond moment. Here we have to calculate bond moment of SH bond. So here H2S structure is this one, H2S. So here the theta value is given. How much? This bond angle theta is equal to 96 degrees. Just we have to calculate mu is given. The value is 0.95 dB of this molecule. Total molecule is given. Now we calculate SH bond moment. Therefore, dipole moment, one formula is there. Dipole moment equal to 2 into bond moment into cos theta by 2. This is the formula. Same formula will apply for this molecule. Dipole moment of H2S equal to 2 into bond moment of SH bond. Here, what apply for this bond only? So, cos theta by 2. Theta value is given 96. So I will substitute. This value is given 0.95. This value we have to calculate. This is the question mark. And this theta value is also given. Therefore, here this bond dipole moment is 0.95 into 2 into bond moment. Just we have to calculate the bond moment of SH and cos theta, cos 96 by 2. Cos 96 by 2, that much? 48. So 0.95 into 2 into bond moment of SH into cos 48 degrees. So here 0.95 into 2 into bond moment of SH into 0.66. So mu SH is equal to, how much we get? 0.72 divide. This is the bond moment of SH bond. So bond moment is also calculated by using this formula. So this is about the numericals. So here we are using three formulas. First formula is dipole moment equal to charge into distance. Second formula is dipole moment equal to 2 into bond moment cos theta by 2. Third formula equal to percentage angle calculated equal to mu observed by mu calculated into 100. So this is the numericals based on dipole moment. Good morning, students. Today we will discuss about last topic of dipole moment. Dipole moment. So here we will discuss about which molecule having more dipole moment. Here I will give example. So CH3Cl, CH2Cl, CHCl3, CCl4. So here, so this is here chlorine, here hydrogen, hydrogen, chlorine and chlorine. So here chlorine, 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 hydrogen, and here same chlorine atoms are there. So here in case of this, it has more dipole moment. So more dipole moment means it is in the same direction, therefore it has more dipole moment. So this is the order of the compound. So this is the order of the compound. And after that, just we are discussing about some more examples of dipole moment. Dipole moment. So here, for planar molecules, mu equal to 0. For planar molecules, mu equal to 0. For non-planar molecules, mu is not equal to 0. Mu is not equal to 0. So which one is planar molecule, which one is non-planar molecule? I will give an example for this. Planar molecules means, so this is benzene. If cyanide group is there here, cyanide group, so this is planar molecule. So the structure is planar. For planar molecule, mu equal to 0. For example, dihydroxybenzene, here dihydroxybenzene, so it has lone pair and also H, and it is non-planar, so it is non-planar molecule. So it is a non-planar molecule. For non-planar molecule, mu is not equal to 0. Mu is not equal to 0. So here SH, here also SH. So non-planar, it is also non-planar. Mu is not equal to 0. For non-planar molecules, mu is equal to 0. For planar molecules, mu is equal to 0. Mu is not equal to 0, non-planar. So non-planar molecules are exhibit polarity and dipole moment. So this is also one of the important. After that, by knowing the dipole moment values and dipole moment, hybridization can be predicted by using dipole moment. Next one is hybridization can be predicted by using dipole moment. So here, how can we find the hybridization? For example, AB2 molecule. So AB2 molecule, example BeCl2 molecule. This is AB2 type of molecule. If A atom can use sigma sigma orbitals only, then its vibration is sp and mu is equal to 0. The shape of the molecule is linear, regular shape. So sp means vibration, regular shape, therefore linear shape. So I will draw the structure of BeCl2 here. So BeCl here. So here using only sigma orbitals are utilized by beryllium. Therefore for this linear structure, so linear and sigma orbitals are utilized. No pi orbitals, sigma orbitals are utilized, and sp hybridization. Then mu equal to 0. Mu equal to 0. In these three conditions, we confirm that its vibration is sp. So for that type of molecules, the dipole moment value is 0. Simultaneously, we are taking one more example. This is first example. And second example, I will take AB3 type of molecule. So, AB3 type of molecule I will take. So, AB3 type of molecule, best example is boron trifluoride. We have three molecules. So boron trifluoride is AB3 type of molecule. AB3 type of molecule. So in this also central atom, boron atom, using sigma orbital for the bond formation. Therefore, shape is planar structure, trigonal planar, and mu equal to 0. Therefore, its vibration is sp2. So here, boron. So like this is the shape of the molecule, planar, and this is planar structure is there here. So therefore, we can predict the hybridization of the molecule also by knowing the dipole moment value. After that, if dipole moment is directly proportional to electronegativity, so this is also one of the points. So dipole moment is directly proportional to the electronegativity. So mu is directly proportional to En. So I will take one example: HF, HCl, HBr, HI. So here, electronegativity of chlorine, bromine, iodine. So electronegativity chlorine, bromine, iodine gradually decreases. Therefore, which one having more dipole moment? It has more dipole, more mu. It has less mu. So dipole moment is directly proportional to the electronegativity. After that, we'll discuss about the molecules having homoatomic molecules. Next one. Homoatomic molecules. Homoatomic molecules, mu equal to 0. Example N2, O2, Cl2. So these are oxygen, oxygen, chlorine, chlorine. So mu equal to 0, mu equal to 0, mu equal to 0. So these are homoatomic molecules. Molecules having normal shapes like linear, planar, tetrahedron. So they are also having mu equal to 0. Normal shapes. I will give an example for this. Molecules are having regular shape or geometry. Example linear, hybridization sp linear, sp2 planar, sp3 tetrahedron. So if they are having regular shape, so example I will give sp hybridization and linear shape is example CO2. For CO2 mu equal to 0. Planar sp2 BF3 mu equal to 0. Tetrahedron CH4 mu equal to 0. Means hybridization and linear same regular shape, but the hybridization is same but the distorted shape. So I will give an example. Molecules are having distorted shape, irregular shape. So molecules are having irregular shape or distorted geometry. I will give an example for this. In SO2, hybridization sp2, shape is not planar, angular shape. Therefore, mu is not equal to 0. Water H2O sp3, shape is not tetrahedron, shape is V shape. So like that, this is also V shape. Mu is not equal to 0 because hybridization sp3 means what is the shape? Tetrahedron, but angular pyramidal shape. Ammonia also. For example, ammonia actual hybridization is sp3, but the shape is not tetrahedron, pyramidal. Therefore, mu is not equal to 0. They having dipole moment. So this is about dipole moment and its application. It is also useful the geometry of the molecule. It is also useful the hybridization of the molecules. Good morning, students. Today we will discuss about applications of dipole moment, part 2. So already few applications are discussed before. Now we are going to discuss about applications of dipole moment. 2. So applications of dipole moment 2 means, so this is also other applications. Already we have discussed some few applications are covered before class. So just we are discussing about some properties also. So NH3 has higher dipole moment than NF3. So this is NH3 has higher dipole moment than NF3. Why? Here this is question. NH3 has higher dipole. When you observe the structure of NH3, so this is the structure of NH3. So here next we'll compare with NCl3 also we are compared. NCl3 also we are compared. And NF3 here this is nitrogen trifluoride. So here the bond movement is in this direction. So here also the bond movement in same direction like this. So therefore in these two cases bond movement in same direction. But in case of NF3, here bond movement is there in this direction. So this bond movement and this bond movement, two bond movements get cancelled. Resultant bond movement is the sum of these two bonds only. Therefore here 4 bond movements are there. 4. This is 1, 2, 3, 4. For example, this is +1, +1, +1, +1. Total +4 bond movement. Example I am giving. Here also same. But here this is +1. This is +1, +1, +1. Here -1. This will cancel. How much we get? +2 only. Resultant bond movement is +2. That means it has less bond movement than NH3. So NH3 and NCl3 because so actually dipole moment is a vector quantity. So therefore bond movement vector quantity means is the sum of the all vectors. So here when you compare these three, so it has more. These two are having more when compared to NF3 because the bond movement in the same direction in case of NCl3 and NH3. So this is also important, one of the application. So by knowing this one, we can confirm the molecules also. So molecules which having more dipole moment, having more polarity. So that is also one of the important thing. After that, second one is cis and trans isomers. Cis and trans isomers also separated. For example, cis isomer and trans isomer, I will explain here. Cis isomer, and trans isomer. Cis isomer and trans isomer. This is cis isomer. This is trans isomer. So here so bond movement is in this direction, in this direction, in this direction, in this direction. Therefore, bond moment is not equal to 0 in case of cis isomer. But in case of trans isomer, here in this direction, in this direction, in this direction, in this direction. So here, sorry, in this direction. So two are, this is and this is get cancelled. This is get cancelled. So in this direction is also there, in this direction is also there. Therefore, mu equal to 0 for trans isomer. So for same direction in this same direction, bond movement is in same direction. So bond direction is in opposite direction. So opposite direction, both will get cancelled here in case of. So what is the use of this dipole movement? Means we are, by knowing cis isomers are having more polarity, by knowing these values, means we can confirm that cis isomer having more polarity than trans isomer. That we confirm that. So this is also very, very important. We know that one cis isomers means identical groups are adjacent to each other. So here identical groups are groups are adjacent to each other. So here identical groups are opposite to each other. Identical groups are opposite to each other. So this is also one of the important. So because of dipole moment, we confirm that so cis isomer having more polarity than trans isomer. In case of trans isomer, opposite directions, identical groups are in opposite direction. Here same direction. So if it is considered as plane, so here same these chlorine atoms are same side of the plane here. Here chlorine atoms are opposite sides of the plane. Therefore, this is also very, very important thing to separate cis isomer and trans isomer. After that, just we'll compare the dipole moment of ortho, meta, para isomers. So ortho, meta, para isomers, just we'll compare which one is having more polarity. So I will explain here. So here cis ortho isomer, ortho, meta and para isomer. So ortho dichlorobenzene, meta dichlorobenzene and para dichlorobenzene I will take here. So here this is ortho dichlorobenzene, this is meta dichlorobenzene and it is para dichlorobenzene. So here when you observe the values for ortho 2.53 divide, for meta 1.48 divide, but in case of para mu equal to 0. So here in this direction we are observing, net dipole moment is 0. So therefore ortho isomer having more than meta than para. So here because ortho isomer having the same direction, so therefore when we compare to this one, ortho is greater than, meta is greater than para. So all para isomers are not having the same type of mu. I will take one example. If the same group here the same groups are there, chlorine, chlorine. So but if you take, so instead of chlorine we are taking bromine. So bromine means, so bond movement is not cancelled by each other. Bond movement not cancelled by each other. So here bond movement is not cancelled. Therefore mu is not equal to 0 in case of chloro bromo benzene. One chloro 4 bromo benzene, it has dipole moment. So like this we can confirm the which one having polarity more, which one having polarity less. By this, by the dipole moment we can identify. So therefore in case of ortho meta para isomer, ortho isomer having more dipole moment than meta and para. So in case of para, bond moment is cancelled by each other. Net dipole moment is 0. So net dipole moment means in one direction +1, in other direction, opposite direction -1. Therefore net dipole moment will cancel by both bond moments. Therefore it is also one of the important. So after that